So, hello everyone. In this video, I'm going to discuss about search trees. So, last time we discussed about maps and then dictionaries, and I have also shown you how you can store those key value items into the hash table and how we can find those keys using some hash functions. Okay, so today we are going to touch on the topic of search trees and primarily binary search trees for this video. Okay, and with search trees, it allows us to search over an ordered universe of key values as well. And in the search trees, however, compared to the hashing that we have discussed before, it allows us to maintain some kind of hierarchy in organizing our information. And well, if we look at the other topics or other uh, d- data structures that we have discussed before, like the linked list, and let's say we want to search key values over it. So a repeated linear search in linked list might be too slow as the amount of data is increasing. And with hashing also, while we have discussed that it's fast because of the just one computation and we can find the key, and it's only useful for mostly find key in operations. And we have also discussed about heaps, but then it's useful only for find min or find max or using these operations to do sorting, for example. Okay, so what if we have more complex operations? Assuming we want to look up by do look up by prefix wherein we type in a few first letters of a name and then we output all names in a database beginning with those letters. If given that we have a lot of data, for example, and then it needs to output a lot of information, right? So you think the repeated linear search would be give us the most efficient running time, or with the hashing where it only gives you find key operations or hips? And then let's say, what if we want to find in range or output all of the keys between key 1 and then key 2, or perform near lookup, like returning the closest key to X when X is not in the database, or finding the kth smallest key, or um, ranking ranking the keys. So with this data structures that we have discussed, like the linked list or the hashing or the heaps, these complex tasks might give you the worst na complexity, or it might not be implemented in the most efficient manner. Okay, so well, thank you to Search Trees, the one that we are going to discuss today, because we can do most of these operations in the worst case, O of log n at time. And how can we do that? With the appropriate na balance ng binary search trees. And with binary search trees, and more specifically the balanced and binary search trees, we are able to perform these operations like searching or insertion, deletion, finding successors or finding predecessors, etc. Okay, so now let us discuss the binary search trees, or the BSTS. Okay, so a binary search tree is a binary tree, and it has a special property. And for all nodes V in the tree, all the nodes in the left subtree of V contain items less than equal to the item in V. And all the nodes in the right subtree of this node V contain items greater than or equal to the item in V. So this is an example. So for example, you are on node 17 and you are on the left subtree and then the right subtree. And as you can see, all of the items on the left of the node 17 are less than the items on the right of node 17. So similarly, the items on the right of node 17 or the root is greater compared to the items on the left of node 17 or the root. Okay? So now let us discuss how we can perform searching in a binary search tree. So to find a value in a binary search tree from the root node, so this is what these are the conditions that we have to check. So if the key value or the target that we are looking for is equal to the value in the node, then we must return the data. But if the target is less than the value in the node, then we will traverse its left subtree. But if the target is greater than the value in the node then we will traverse its right subtree. Okay, so very easy. So if we compare the key value that we are looking for with the node, or let's say the search with the node or the root rather, and if it is less than the root, let's say we go left, but if it's greater, we go right. Okay. If null value is reached, then we return null, or in other words, we have not found the key or the item. So how many comparisons will there be? So the one for each node on the path, and on the worst case, we will be reaching the height of the tree, or we will reach a certain leaf or a node without any child. And that's the time that we have concluded that the item does not, or the node, or the key target that we are looking for does not exist in the tree. Okay, so let us go on or continue to with the BST insertion, and well, we are still going to make use of this algorithm for BST search and BST insertion. Okay, and in the BST insertion, the very basic, we are going to insert a new node in the tree, but we must the property of the binary search tree must hold after the insertion. So, and what's that property again? So all the nodes in the left subtree of V contain items less than or equal to the item in the V, or all of the nodes in the right subtree of V contain the items greater than or equal to the item in V. So if we want to insert an item, so we must make sure that this property is held, okay, or maintained. So therefore, the new node must be inserted in the correct position. And this position is found by, of course, as I have mentioned, making use of the BST search, or we must check this following the conditions and do the decision accordingly. Okay? So if the search ends at the null, the left child of a node, then make left child of a node make its left child refer to the new node. But if it ends on the right child of a node, make its right child refer to the new node. I will show you later how it is done. Okay? And what would be the cost of the BST insertion? So still, it is the same as the cost for the search algorithm or the O of height. Okay, and in binary search tree, it's log n. Let's see the BST insertion example. For example, we have this tree, and then the root node is 47, and then this is the left subtree and the right subtree, and then as you can see, if we look at the keys on the left, these are all less than the keys on the right subtree of 47. Okay, let's look at 32. Now we are at 32, and if we look at its subtree, which starts at 19, and then on the right subtree, which has the root node 41, we can see that the right subtree are all greater than the items on the left subtree of 32. And this is true for every other node in the tree. So for example, let's look at node 96. As you can see, 96 has only children 91 and then 97. So on the left subtree of 96 is 91, on its right is 97, and the right subtree is always greater. Okay, now moving on or going back to our example, we want to perform an insert na operation, and we want to insert this 43. So what are we going to do? We are going to create a new node, and then we are going to find the position, and then we are going to insert that node into the tree. Okay, let's start. So we create a new node, 43. Okay, now we must find the position. So we start with the root. Now 43 is less than 47. That means that we have to go left. Okay, now we are now at 32. Compare again. 43 is greater than 32. That means that we are going right. Okay, now we are now at 41. Now, compare again. 43 is greater than 41. That means that we are going right. Okay, now we are going to insert the item here. We were at 44, and we know that 43 is less than 44, so we are going to add a new node on the left of 44. Okay, so we are going to add 43 on the left rather of 44. Okay, on the next video, I am going to discuss about deleting a certain node in a binary search tree.